So now we're going to talk about why ropes are always in tension, in the same tension no matter where you are in the rope. So imagine we have this sad looking guy. He's leaned over lifting this 10 kilogram block with a rope. So let's first of all draw a free body diagram and see what's going on. So we need free body diagram. So we're going to have the block here, just like this. Its weight is going to be pulling down, and it's equal to mass times g. And the tension in the rope is going to be pulling up. And that's all there is acting on this block. There's no other forces. So we can go ahead and we can find, we'll say the sum of forces in the y direction is equal to 0. There's no forces in the x direction, there's no moments, there's nothing else going on here, just two forces acting on it through the mass center in the y direction. So all we have to do then is add up the forces. So let's call this tension. So we will say that, and again we'll say that this is x, y. So up is going to be the positive y direction. So we will have the sum of forces, so we'll have tension going up minus weight is equal to 0. But we know what weight is. Weight will be 10 kilograms times g, so 10 times 9.81, 10 kilograms times 9.81 meters per second squared equals 0. So we can simply move that over to the other side and we'll get tension is equal to 98.1 newtons. Alright, and that is going to be going in the upward direction. Or you don't have to specify the direction because the fact that this is positive, we'll know that it's going in the positive y direction. If it was negative, it would be pointing down. Okay, so now that we know, let's just label this here. So tension is equal to 98.1 newtons. Now as long as tension is equal to 98.1 newtons, that's going to perfectly, and that it's going straight up, that's going to perfectly cancel out the weight that's pulling down. Right? So its weight is equal to 98.1 newtons. Okay, so what happens if, so see, notice, let's draw, right now he's holding at this level. So if we go ahead and we just erase him, we'll delete him like that, and we'll bring him back. Now what if he's holding down at this level? Okay, well, he's still pulling straight up on the rope, and the rope just got shorter, but this block still weighs 98.1 newtons. And so in order for it not to move up, or in order for it not to move down and stay in place, he has to pull up on it still at 98.1 newtons. Notice now he's pulling at this level. Okay, and I'm sure you can see that now if we just put him anywhere along this line, as long as he's pulling straight up, in order for this block not to move, it just has to, the tension has to be 98.1 newtons. So that means the tension at this level is 98.1 newtons straight up, and the tension if it was up here was 98.1 newtons straight up. Okay, so now we're kind of getting somewhere. What if it goes around a corner? So let's delete him. Let's get rid of this. And now we're going to get a little crazy. So we'll say that this is still going straight up, minus my crookedness in the drawing. Okay, so what if it hits a pulley? Like this. We're going to draw one of these frictionless pulleys that we like so much. Okay, bear with me. It's going to go around the pulley, and it's going to go down this way. Okay, so now this is similar to the last video that we had a pulley like this. So we have tension in the rope, and I claimed that tension over here was still the same. Well, if we draw a guy again, conveniently he keeps appearing. Oops. Oh, having some technical difficulties. There we go. Alright, so we're going to draw him holding the rope like this. Alright, he still looks pretty upset because his back is probably pretty sore. But now if you look at this, well, you might think that it would be a different tension. That you would have to be pulling it different because there's a pulley and it's changed directions. But this block still needs to be supported by 98.1 newtons, which is still 98.1 newtons here. And the only way that this guy can do that is if he pulls on this rope with 98.1 newtons, then this whole rope will be in tension, and you'll see it'll still be pulling here at 98.1 newtons. So you could say that, well, he's pulling the rope this way right here, at 98.1 newtons. And because the rope is also in static equilibrium, the rope's not moving, then the rope has to be pulling back on him in the equal and opposite direction at 98.1 newtons. And then you'll see that the tension here is still 98.1 newtons. So we could draw this guy in any sort of configuration. We could draw another pulley pulling up in some weird direction. But as long as the pulleys are stationary and not moving, then we'll find that this tension is always going to have to be 98.1 newtons in order to support this 10 kilogram block.